for the invitation to do this, is to give you a brief introduction to VHF Meteor Scatter. Are you seeing my slideshow on the screen?
Not yet.
Ah, okay. Let's see what's happened there then.
I don't know what I was trying to do. It's not yeah, we're sorted now, almost. So where's the sharing?
Let's see. It should be on.
Here it comes. All good. Just into presenter mode and probably swap it again.
I'm not seeing the lecture up on the screen now. I can see my own face, but I can't see.
Just minimize the Zoom screen or move the Zoom screen.
Oh, there we are. Now I can. Have you got the first slide of the lecture now?
Yes, we do. We're all good.
Okay, that's good. So I'm going to give you a bit of an introduction this evening to VHF Meteor Scatter, something I've been interested for quite a few years. And this is, as I say, it's an introduction. This is not intended to be a masterclass for people who've already had a considerable experience of this. I'm quite humbled to think that there may be people watching who know far more about this than I do. This is aimed for those who have either never done any meteor scatter or those who've had pretty limited exposure, with the hope that we can get a few more people to come up and give it a try. First thing I want to say is that I am not a radio tech. I'm not an engineer. I've had no formal training whatsoever in any aspect of electronics or computing. My background is that I'm a medical practitioner. I'm a specialist anaesthetist by background, and I've spent most of my my career giving anesthetics and intensive care for people having open heart surgery. So it's a long way from meteors, I'm afraid. But what I always say is that I've been a ham for far longer than I've been a doctor. And in fact, this is my 50th year of being licensed this year. So that's a bit of a milestone for me. Anyway, let's have a little talk about meteor scatter. I'm going to start talking about meteor scatter based around 2 meters. 144 megs, but we will touch on other bands where that's appropriate later on, see what's possible. We're going to do a little bit of radio, a little bit of astronomy, a bit of physics maybe, tiny bit of maths, just to make this all come together. Now, if you've only ever used 2 meters as an FM mode from your car or through a repeater, and it's very good for that. You know, it's a great little way of keeping in contact with all of your local hams, but it's only really scratching the very surface of what the VHF bands are capable of doing. Generally, 2 meters in that respect is a line of sight mode. You can work as far as you can see and a little bit more. But if you've been on the bands for any length of time, then you soon know that just occasionally you can get much, much greater distance. Now, when you get DX modes of propagation on VHF, the normal 30Ks can track out to hundreds and sometimes thousands of kilometers, and you can make contacts over a great distance. And most of my interest in recent years has been to push the envelope out to get the very utmost in distance and contacts on the VHF and the microwave bands. That's currently what's pushing the boat out for me. But over the 50 years or so that I've been doing this, I've had a crack at most things. So when you do get really long distance propagation on 2 meters, the usual mode of propagation is with tropospheric ducting. So this is a summertime phenomenon where you get high atmospheric pressure and very still air, and ducts form in the upper part of the troposphere. That's the bit that we live in, where all the weather is. Our 2 meter signals can get trapped in those ducts or microwaves, and they can be transmitted over considerable distances, thousands of Ks sometimes, with very low attenuation. On 6 meters, still VHF, the commonest real long distance mode of propagation is sporadic E, which is an ionospheric method of propagation where there's such intense ionization going on that it not only supports propagation for the HF bands, but it does the same up into the VHF spectrum. There are other modes that can conduct VHF over great distances, including satellites, if you retransmit from them, aircraft enhancement, And I suppose the ultimate is EME, where you use the moon as a passive reflector to get your signals round to the other side of the Earth. You can certainly work into the USA on 2 meters or on 10 gigs, in fact, and to every other continent. But the mode of propagation that we're going to talk about today is meteor scatter. And before we go any further, I just want to define a couple of terms for you. What's the difference between a meteor and meteorite? That's the first place to start. Now, this is a meteor, and we've all seen, if you've been out at night, on a clear night, you almost certainly at some stage will have seen one of these. This is a shooting star, or sometimes called a falling star, even a wishing star, because if you see one, it's supposed to have magical significance, and you'll be able to wish for that new 7851 radio that you want, or that new microphone that Hayden's got, just by seeing one of these. And these are caused by tiny particles of extraterrestrial material, so a bit of rock from outer space, in other words, being drawn into and accelerated by the Earth's gravitational field and burning up when it meets the upper aspects of the atmosphere. So a meteor has to be completely ablated, completely burnt out. Meteorite, to contrast that, is a piece of material coming from outer space that's made it all the way down to the ground. So if it's on the ground or it's hit something, it's meteorite, not a meteor. If it's a meteor, it's been burnt up completely in the upper atmosphere. Now, here's a bit of meteorite. This one's on display. I'm not sure if you can see that. This one's been on display in the Smithsonian Museum in the States. It's several meters tall. There's a person standing beside it here just for comparison. And you can see that it's got an effectively a smooth surface, and it looks metallic because it is. Most meteorite is composed of metallic iron or metallic nickel, and inside spaces within a meteorite, there's often large empty holes. And when this thing was in flight, that would have been filled with ice, either solid water or solid methane. So big pieces of meteorite, you can often find them on the ground, particularly in desert areas where there's no undergrowth, because the chemistry and the appearance and the geology of these things is entirely different from all the local rocks. And being made of iron, a lot of the very earliest iron workings that was made by mankind were made from bits of meteorite and heated up and bashed into various tools. So that's the difference. Meteorite hits the ground, meteors are burnt up on entry. Now, meteor scatter propagation involves reflecting your radio signals off the ionized trail that's left behind when a meteor enters the atmosphere. So these tiny fragments of rock get drawn into the Earth's gravitational field, and they're accelerated, and they accumulate kinetic energy. And as they approach the ground, they eventually will meet the first part of the atmosphere, where they start to meet resistive forces from the air and frictional heating, and eventually they'll be completely ablated. Now, the first part of the atmosphere that's capable, is dense enough to actually cause enough air resistance to slow these things down and dissipate the kinetic energy, is at about 100 kilometers in altitude. And if you remember, 100K, that's roughly the height of the E layer. And in fact, the very existence of the E layer as we know it is at least in part responsible for or being caused by the metallic nickel and iron that's being distributed from meteors being ablated. Now, by virtue of the height of that layer and the curvature of the Earth itself, signals that are leaving the ground and being reflected from these ionized trails, the maximum distance that they can go is roughly 2 and a bit thousand kilometers. Then that's just because of the geometry of what's got to happen. Now, when you use meteors for radio propagation, meteor scatter propagation, if you will, your signals are not reflecting off the meteors. That's incorrect. The meteors are far too small. They don't have enough mass. So it's not being reflected off the meteor itself. It's also traveling at velocities that would put a 2-meter signal down into the medium wave probably. What you're actually reflecting off is an ionized trail that's left behind. And the ionized trail is not the metallic ions from the meteor itself. They're caused by the superheating of a column of air ahead of the meteor. When it comes in, enormous velocity, all that kinetic energy is dissipated, and it will raise the temperature of a column of air in front of the meteor to the point where it becomes incandescent and starts to glow. And in doing so, what it actually does is it shocks the free electrons from the outer shells of the air molecules out into free space. And it's the free electrons that are actually reflecting the radio signals. The higher the concentration, the higher the density of those free electrons means that more and more signal is reflected to ground. The longer the track will persist, and also the higher the frequency that can be reflected off the trail. Now, from meteor scatter for ham purposes, there are actually two distinct types of reflection that we're interested in. The commonest type by a large country mile is what we call a ping. And a ping is a very, very short period of propagation, usually around about 100 milliseconds or a tenth of a second on 2 meters. That's just about enough to get one dit through on CW or one syllable on SSB. So it's there and it's gone. The second type, which is far rarer when there's a larger piece of meteor coming into the atmosphere, where there's a higher concentration or a higher density of free electrons, is called a burn. And the burns can support propagation for 10, 20, 30, sometimes more, sometimes hundreds of seconds at a time. And here's the characteristics that we see of both the ping and the burn. In the upper panel here is a ping. And it's characterized by a very, very steep upflick in signal intensity on the ground, followed by a very rapid exponential decay back down to threshold. And that's really just tracking the temperature fall of the superheated air and the reamalgamation of free electrons back into their parent gas molecules. And that's only lasting around about less than a second. So most of them are about 0.1 of a second. Now, in contrast, the effect of a burn is that you get a very steep rise initially, and that's followed by a much slower rise to a higher peak, and eventually an exponential decay. But it could be 100 or more seconds later. But the entire trace is characterized by this fluttering intensity, which is very similar to that you get with aircraft enhancement. And in fact, it's for the same reason. The very large meteors produce a cylinder or a cone of ionization in the upper atmosphere. So it behaves not like a single point of reflection, but by a long thread of reflection. And at some points, the signals are in addition, in other parts they cancel out. So this fluttering is characteristic of a meteor burn. Now, here's an interesting photo. This is a photograph of a meteor trail, but photographed from above. This was photographed from the International Space Station. As we said, meteors get ablated at around 100 kilometers of altitude. The International Space Station's up around 500 kilometers in altitude. So it's actually looking down at this point. It's looking down onto a meteor trail in at about the height of the E layer. Let me just get to the next slide. So when do meteors come? Well, there's two types. So there's two events that we need to talk about. There are random meteors that occur every hour of every day, and then there are meteor showers. So let's talk first of all about random meteors, because these are the commonest. These are the ones that we mostly rely on. Now, meteors come every hour of the day, 24/7, and they come on every day of the year. Now, most visual meteors that you would see, you only see at night. But the reason that you see them is not because they're not there in the day. They are there in the day, but the faint traces are completely overwhelmed by daylight. For the same reason you can't see stars in the day, you can't see optical meteors in the day either. There is, however, a peak that occurs in the pre-dawn period, and we'll discuss later on why that's the case. And there's a corresponding lull in the afternoons. There's a peak in meteor and usable meteor activities during the spring seasons of the year, and there's a corresponding lull that occurs during the autumn periods of the year. Now, the meteors that we are interested in from a radio perspective are tiny fragments of rock that have a mass somewhere between 0.1 of a gram and about a gram. So we're talking about little rocks from about the size of a grain of sand to something around about the size of a dried pea, just to get some perspective. And to be ablated at the 100-kilometer level, they need to have an entry velocity of somewhere between 10 and 100 kilometers per second. Now you notice this is kilometers per second, not meters per second. And you'll know from schoolboy physics that kinetic energy is proportional to velocity squared. So if you increase the velocity of something by a factor of 10, its kinetic energy that you have to get rid of if you want to slow it down is increased by a factor of 100. And if you go from meters per second to kilometers per second, 1,000-fold increase, then that's 1,000,000 times more energy that's being supported. Meteor showers are something quite different. Now, it's been recognized for centuries that meteors, the optical meteors, don't come the same every day. And it was recognized that on some dates in the year, the number of meteors is enormously enhanced. This picture here is from a woodcut which is in the Louvre in Paris, and it depicts the Leonids meteor shower in 1833, when there were thousands and thousands of meteors every hour were recognized. And there was widespread panic across Europe because it was thought to be a sign of impending natural disaster. So there's a couple of interesting features that is different about meteors that come during showers. First of all, as we've said, there are very large numbers of them. They come on extremely predictable dates. In fact, they occur every year, century after century, on exactly the same date. And they occur when the orbit of the Earth around the sun takes it through a track that's been previously followed by a comet, that's crossed our solar system. So as a comet comes through the solar system, it leaves behind it an enormous trail of rock and gas and crap. And every year on the same date, we go through that same trail time and time again. Now, our position in the orbit around the sun is what determines the date. And so because we go through that track the same time each year, that's because that's where the date is. That's what defines date. And the position of the various star constellations for the same reason. They're always appearing in exactly the same spot in the sky on a certain date. So from tradition, the meteor showers are named by the constellation where they appear to come from. And that's the other interesting thing. This picture that I'm showing you here now is a time-lapse photograph of the Orionids meteor shower. Now, in the center of this, those who know have ever looked up at the sky, the constellation of Orion with his belt here with the 3 stars and his sword, that's probably the second most recognizable constellation in the southern sky after the Southern Cross itself. And you can see that all of these meteors appear to be coming from the center of that constellation, and that's why it's called the Orionid shower. Now, there are about 11 of these meteor showers each year, major showers, and when one of these is running, radio enhancement is enormously increased. Here's a list of the commonest showers that we use for radio work down in the southern hemisphere. The 2 real major ones are marked in red. We have the Lyrid shower coming up later this month, incidentally. A big one in May, the Eta Aquarids, appear to be coming from the constellation of Aquarius. Now, obviously, the meteors are not coming from the constellations themselves. They're not coming from the stars. They're hundreds or thousands of light years away. They only appear to be coming from them because of a fluke of the geometry of the Earth going around the sun. The other big shower is the Geminid shower in December. So there's the dates of the major showers. And when they're on, it can almost be wall-to-wall communication on 2 meters, particularly 2 and 6. Now, how much material actually comes into the atmosphere each year from outer space? Now, even the most conservative estimates would suggest that there's between 100 and 150,000 tons of extra terrestrial material coming in every year. And if you divide 100,000 tons by the mass of a grain of sand, that'll give you some idea of how frequent that meteors really are. All right, so you might say, so okay, you're on 2 meters and you get a signal from 2,000 kilometers away on 2 meters that lasts just 100 or 1/10 of a second. How are you going to get a QSO out of that? How do you actually convert that phenomenon into radio contacts? Now, back in the 90s, 60s, and 70s, the only way this could be done was by the use of high-speed CW. Now, bear in mind, in the 60s and 70s, there were no home computers, there was no internet, there was no transistorized equipment to speak of, and there was certainly no way of doing this electronically. So the only way it was done was that they used a mechanical keyer to send up to 1,000 characters per minute, a little short string, repeatedly sent and then received at the other end by somebody with a multi-speed a reel-to-reel tape recorder, and you'd record that as best you could, and then you'd play that back at slow speed to try and decode any CW that was caught into it. So it did work, but you'd have to be a super geek to be able to do that. Now, that all changed in the year 2001, and all changed because of this guy. This is Joe Taylor, Professor Joe Taylor. He's an emeritus professor of astrophysics at Princeton University in the US. He's a Nobel Prize winner. He won that for all his work on pulsars, the radio stars, but he's also a radio ham, K1JT. And in 2001, he gave to the amateur community a suite of software to allow them to make use, using home computers, of very rare and difficult modes of propagation. The suite of software he produced was initially called WSJT, Weak Signal Joe Taylor, and in it were several modes that relied on computers to do all of the legwork. And so the principle of all these things is that you use a computer to generate audio tones for you, which you then transmit through an unmodified SSB transmitter, through whatever mode of propagation you're trying to work on, and you use the receiver side to receive the tones, and then the computer to convert the tones and decode them back to plain text. One of the modes he put into the system was one of the slow modes, JT65, still in use today. It was used initially as a method of doing EME with a small station. Now, up until 2000, the EME was the province of the superstation with massive antennas and power and a lot of money and real estate. Joe Taylor, with his JT65, turned EME into something that normal mortal hams could do with just their ordinary backyard antennas and basic unmodified ham stations. But that mode found another use. It was soon realized it had other uses other than EME, and it was soon being used on HF for getting long distances with very small powers. Now, for Meteor Scatter, he generated this mode, which was called FSK441, and this was one of the fast modes. This rattled on at 40-something baud, and it was particularly aimed at Meteor Scatter, not for weak signal work, but for short signal work. And had I been given this lecture even 2 years ago, FSK441 was the digital mode that was still the mainstay of digital Meteor Scatter. It's been superseded now, but because it's so fundamental, if you understand the principle of what this does, then you'll be able to easily transfer to some of the later modes. So FSK441 worked by transmitting one of 4 audio tones at about 41 baud. So that sounds a bit like a machine gun sort of rattle when you hear it on the air. And the 4 tones are included and transmitted easily by a totally unmodified normal amateur SSB transceiver. And it worked on a 43-character alphabet. And because of the maths and the physics of this, it took 3 tone intervals for each character. Those 43 characters, incidentally, is all the letters and numbers and a number of extra characters. And the idea was that you would put together a short string of information. It could be only 23 characters long, which is enough for 2 call signs and a grid square, or 2 call signs and an exchange report. And you would transmit this regularly on alternating periods of time. Now, for those of you using FT8 or whatever on HF, you'll be fully familiar with first and second periods. The original FSK 441 used 30-second periods. And so you are either receiving or transmitting at any instant, and you just had to select to make sure you're in the right period. We'll come back to that again in just a minute. Now, in 2018, that mode was rendered virtually an heirloom facility. There were 2 new digital but forward error correcting modes that were introduced. We weren't sure at the time which one of these 2 would take off, but in fact it's the MSK 144 mode that's taken pride of place. It's now the king. That mode's available in several software suites. It's forward error correcting, which means you either get a complete perfect message or you get nothing. But because it was so much better at decoding than even its predecessor, which was pretty good, it's now allowing us to decode reliably pings off meteors that are substantially shorter than the 100 milliseconds that we can frequently get. And it's allowed us also to switch down to 15-second periods, which is much easier on your PAs, I can assure you, than key down for the 30-second periods. Now, I'm just going to touch on one other feature that, again, is common to all digital modes, and that is what actually constitutes a QSO. What do you actually have to get through to have a valid contact? And this is something that's now pretty much agreed worldwide and what's actually required. The first thing is that there has to be an exchange of the call signs between the receiving and transmitting stations in both directions. There has to be an exchange of signal reports. And at the end of this, there has to be a confirmation that all the necessary information has been transmitted between both stations. In some part of this, there has to be an exchange of something that can't be predicted by chance. And normally that signal report fills that criteria. So as long as you get the call sign signal report through, that's what qualifies as being a valid QSO. And that's common to everything. That's been common to EME when CW was used. It's common to all the common digital modes that are in use now. So a typical Meteor Scatter QSO in digital form would run something like this. Like most QSOs, they start with a CQ somewhere. So in this one, I'm in red. So I would send out a short string continuously, CQ, my call sign, and my grid square. And I would continue to send that every 15 seconds until somebody receives it. In this case, it's Ari down in Melbourne. He's picked me up, and what he sends back to me, sends my call sign. I know it's for me because it's the first one. He sends me +5, which is my signal report in dB above noise, and then his call sign. So the first one is the destination. The second call sign is the source. And he would continue to send that report to me until I get it. When I see that, then I say, okay, well, I'll send this back to you. I send VK3ZL-R01. Now, in this context, this is something that was picked out of EME protocols from 50 years ago. The R means Roger. That means I've received my report, and my report to you is 01. So you're 1 dB above the noise. Once that, and I'd continue to send that until he receives it, at which point he would reply with RRR. Now that's Roger, Roger, Roger. I've received all the information that's required. And at that point, the QSO is actually complete. But of course, Ari doesn't know that. And so to allow him to move on and work somebody else, I can send the 73. It's only a courtesy. It's actually, the QSO is actually complete at the RRR stage. And that's the same with all digital modes. So how far can you work with Meteor Scatter on 2 meters? Well, what I've done here, I've overlaid on a map of Australia based on Brisbane 2 concentric circles. The first is at 1,000 kilometers. And the second one is out at 2,000 kilometers. Now this first ring, this is what I call the easy zone. Now, from meteor reflections off the ionized trails, the loudest signal comes when the meteor trail crosses the path between the two stations at right angles and exactly in the midpoint of that path. But inside this 1,000 kilometer zone, there are lots of different ways that meteors can run, lots of different potential tracks that will still get a signal through. As you progress from that line out to the 2,000 kilometer, things get progressively more difficult. When you're at the absolute limit, so out at the 2,100 kilometer level, the meteor trail now has to be exactly at 90 degrees to the path between the two stations, and it has to be exactly at its midpoint, otherwise the signal can't get through. Now you can see in that inner easy zone, from Brisbane, I can easily work into VK2, I can work into VK1, I can work down into VK5 with ease. In the outer circle, I can reach VK7 and probably the borders of VK6. But from Brisbane, at least, all of the major population centres are beyond my reach. I can't work into any of the New Zealand cities. If you live in Sydney, you can do that any day of the week. But from Brisbane, you can't. And yet I've worked lots of stations in New Zealand on Meteor Scatter, but it requires you to have another mode of propagation running at the same time. And usually that's caused by is when you get a little bit of tropoducting at either one or both ends of the path, and that fills in the gap between, that just fills in the gap of what Meteor Scatter can't bridge. Now, anyone who's done any of the current digital modes will be familiar with the waterfall display. And I'm sorry, this was a moving display, but it's not going to play on this screen today, so I apologize for that. Now, normally, waterfall displays used for things like FT8, they have a frequency axis along the top with low pitches on the left-hand side and high frequencies on the right. And the waterfall itself tracks from top to bottom. And any signals that are detected appear as lines in the screen. Now for Meteor Scatter, we actually turn it on its side and the other way around. So the waterfalls run from left to right in the Meteor Scatter modes. This one's halfway through, and you can see that there's a line that's appeared here at about 3 seconds into the period. The bottom traces an S-meter equivalent, an intensity or an amplitude signal. And you can see it's got all the features of a ping. You can see a line from a ping, and you can see that shape with the steep uprise and then the exponential decay. So that's what a ping looks like when you receive it on Meteor Scatter in the waterfall. Here's a burn. This one you can see is run for at least 15 seconds or so. And in fact, it's running probably into the next transmit period. And it's got the characteristics that we talked about. It's got the sharp rise time, it's got the fluttering intensity, and then exponential decay at the end. And above it, you can see that this is actually from Colin, 5DK down in Mount Gambier, who was coming through on 2 meters on this occasion. So when do we operate Meteor Scatter? Well, you can do it any day of the week you like, any year of the day, any day of the year as well. But we do have 2 activity periods every week, and they're run on Saturday and Sunday mornings to take advantage of the pre-dawn peak that we talked about. We normally run those before the sun is up. Now down in Sydney, that's the 7 o'clock area. But up here it's a little bit earlier because we don't have daylight saving here. And those 2 operating sessions, they run for 1 or 2 hours until propagation falls out of the screen for us. Now we all the operators who are working on Meteor Scatter work on these 2 specific focus frequencies that are in our band plan. So on 2 meters, the focus frequency is 144.23, and on 6 meters it's 50.23, and all stations operate on exactly the same frequency at the same time, and we'll discuss how that's possible in just a minute. The most important thing to get a handle on if you want to have a go at Meteor Scatter is which period should I be operating on. Now, what is obvious is that if you want to have a contact, the 2 stations involved have to be in the opposite periods. One must be transmitting while the other's receiving, obviously, or you're never going to get anywhere. What isn't quite so obvious until you think about it, is that you have to be in the same period as well as all the other stations who are operating in your area. Because if they're within local range of you and you're in the wrong period, you're just going to flatten their receiver when they're trying to receive, and they'll do the same to you. So we have developed over the years a protocol for who goes into which period. And it's pretty simple. It's not perfect, but it does allow us to work as many stations as possible. And it works on the principle that all the stations who are up here in the north, like in VK4, we always run in the second period, and we always beam south. Those stations in the southern call area, so 3, 5, and 7, they do the opposite. They always transmit in the first period, and they always beam north. Stations in the middle call areas, VK1, VK2, they change the period that they're in, depending on whether it's Saturday or Sunday. So on a Saturday, they join us up here in the north, they transmit second and they beam south to work the southern guys. And on Sundays, they flick over and they work in the first period and beam north up here to work us. So it's very important that you get a handle on where you are and which period you're in, because if you don't get it right, it all grinds to a halt. What sort of equipment and station do you need to have a go at Meteor Scatter? Well, the first thing you need is an SSB transceiver, and just about anything will do for this purpose. Anything that's good enough and stable enough to give you an SSB contact will be good enough to do Meteor Scatter. Because there's some Doppler involved in the process of meteor propagation, then the software will allow you to be further off frequency for meteors than it would be for SSB. You can decode a Meteor Scatter digital signal that was so far off that you wouldn't be able to copy it if it was in SSB. Next thing you're going to need is a computer of some sort to actually generate the audio tones and to take them in and decode them. And just about anything will do for that as well. The processing power required is very modest indeed. And just about any laptop or computer that's got an operating system that's still supported will be good enough. Even Arduinos or Raspberry Pis can be pushed into this sort of service. To run MSK on 15-second periods doesn't need that much fancy computing power at all. Next thing you're going to need, of course, is you've got to get some way of getting the digital signals, the audio signals, in and out of the SSB transmitter, whether that goes through the microphone socket or some individual other audio levels. That all can be done. There are lots and lots of homebrew ways of doing this, and they're all common to all the digital modes. So anything that you set up to do slow scan TV or packet or any of the other digital modes, once you've got that set up, it will work for this as well. So what it has to do is transfer audio in and out of the transmitter. It's got to get the levels right so you're not overdriving anything. It's got to be protected from hum loops and RF sensitivity. And of course, it's got to be able to drive the PTT. The computer has to be able to command the radio in to transmit and receive at the same time. This picture here, I used to use these signal links for many years. They're basically an outboard USB sound card connected to the your computer with a USB cable and does all those functions for you. Some of the later and the current models of rigs from all the manufacturers have got sound cards built into them. This is an ICOM 7851, that's got one in. The 705 has got one in. And this is capable of running audio in, audio out, PTT control and CAT control down a single USB cable with no intermediate amplifiers or level adjusters or anything else. It'll just do everything. And the WSJT and MSHV software are already got all the drivers built into them. You just tell them what radio you've got and it does all the work for you. Next thing you're probably going to want, if you're going to do this seriously, is you're going to want an intermediate amplifier to just raise the power level. Now, the power limit for digital work in Australia is currently 120 watts, a bit lower than for SSB, but even the best 100-watt SSB rig is not going to be able to run key down flat out for long periods of time like this. That sort of duty cycle will overheat the PAs, cause drifting, distortion. And so most people would put an intermediate amplifier to get up to the power limit, while running the actual transceiver at a lower rate. so as not to experience any of those problems. And the final thing we need to talk about is antennas. That's a slightly different issue. Now, for most DX on VHF, most people will go for the biggest antenna, the highest antenna gain that they could get, so you get the best signals on receive and transmit. But for Meteor Scatter, that's not necessarily the way to go. By virtue of the fact that the signals that you receive off meteor trails don't come in general directly on the path between the two stations. In fact, statistically, most of the returns occur on either side of that direct heading into what we call the two hotspots. There's a hotspot A and a hotspot B, about 10 degrees or so either side of the direct heading. Interesting enough, the software will tell you which one of those two hotspots between you and another station is most likely to give you the best results. But an antenna that's too big and has too narrow an aperture will actually lose you more signals because you're missing them off the side than it will gain. This is a 14 element Yagi that I'm using at my station, and 8 was probably the sweet spot, and that's where most people go. Should be horizontally polarized because meteor scatter propagation favors horizontal polarization, and it does not require any elevation control. Unlike satellites and EME, it's not required. The real long distance signals that you're interested in are going to be coming in ground scraping. They're going to be coming in at 0 elevation. So a simple horizontal dipole is what you want, and around about eight elements is probably close to the optimum. Now, what we've described so far is really no different to any good SSB station on 2 meters. There's been nothing new added in there. The only other thing that you do need to address is you need to be able to control the time of your computer clock. For the meteor scatter modes, you probably need to get the clock and keep it within 1 second of true time. Lots of ways of doing that. If you're internet connected, there are plenty of apps that will keep your computer clock up to date. Lots of different pluses and cons. If you're out portable without internet connection, you can derive the same signals from GPS sources to do the same, but you do need to be fairly accurate, because if only to stop deafening all your neighbors by coming up early or late. Okay, you might say, nah, this is still not going to work. If you've got 5 stations in Brisbane and 5 stations in Melbourne, all transmitting back and forth to one another, when a meteor comes in, there's going to be a big flash, and all I'm going to see on my screen is 5 different stations all piled up on one top of each other, and I'm not going to be able to decode one from the other. Well, actually, you can. You can separate them out. Now, the reasons for this are quite complex, and we don't have time tonight to go into everything, but there's a phenomenon called geospecificity. And what that's actually saying is that even stations who are only separated by a few tens of kilometers, at a distance of 2,000 kilometers away, the signals don't pile up one on top of the other. They're often separated. So 2 stations A and B in Melbourne, on one ping I would hear and decode station A. On another ping I'd decode station B, so I can separate them out. Often you get responses from both A and B, but they're separated in time. The path lengths are different. It's a very sharp phenomenon reflecting off the meteor trails. And so you can actually unravel all of these different stations. Sometimes you can get 4 or 5 decodes all in one sweep of the period and decode them all separately. And you can continue to work them. So they don't. I'm not going to go into that one. That's too complicated for this tonight. The next question that people often ask is, why are there only meteors at dawn? And in fact, there aren't only meteors at dawn. Meteors are coming every hour of the day. But there is a reason why there's that peak in the pre-dawn period of meteors that we can use for meteor scatter. As you may know, all of the planets in our solar system are all on their own separate orbits, orbiting around the sun. But all of those orbits, more or less, are on the same plane. So it's like all of the planets are running around on a racetrack. And here's a racetrack. So if you imagine that we're looking down on this, the sun is in the middle of here, and the Earth is running around the track, along the track of the blue arrow. And we go around that orbit once every year. That's the definition of a year. Now, this is a bit of a busy slide, but just bear with me a minute. What we're doing here, we're looking down on the top of the Earth. So that's the North Pole at the top, and the sun is up here at the top of the screen. Now, the Earth is rotating around its own axis, and the Earth is rotating around its another axis around the sun. So it takes 24 hours to make one rotation of its own, and it takes a year to make a rotation around that plane. Now, from the point of view of somebody standing on the equator on the surface of the Earth, the very rotation of the Earth around its own axis means that it's actually moving through space at around about 35 kilometers per second, just by virtue of that rotation, I'm sorry. The movement of the Earth around the sun along this arc means that that is also moving in space at around 30 kilometers per second by virtue of that motion. Now, around here on the sunrise side of the Earth, those two velocities are acting in the same direction. So they're being added together. So from the point of view of things happening here in the pre-dawn period, that's approaching a velocity through space of the surface of the Earth of around about 65 kilometers per second, which is very close to the velocity that the meteors have to approach in order to ablate at the 100-kilometer level. And that's why most of the meteors that we get are occurring in this part of the globe. Around on the sunset side, of course, the two velocities are in opposite directions. There's one going in that direction, but the Earth is turning against it. So the combined velocity is only around 5 kilometers per second, which is too slow for the meteors to get ablated. So it's rather analogous to bugs hitting the front of your car. They all hit the front windscreen. It's very rare to get bugs hitting the back windscreen. Let's talk a little bit about other bands and other frequencies. Now, you can do meteor scatter on higher frequencies and lower frequencies. You can even do it down to 10 meters. There's a little bit of physics that applies. As you go up in frequencies, it becomes more and more difficult. The free electron density has to be much higher, and the pings get shorter and the signal strengths get lower as you go up in frequency. The ping duration, that's how long the ping lasts, is proportional to the wavelength squared. So if you go from 2 up to 70 centimeters, the wavelength's gone down by a factor of 3. So a third squared is about a ninth. So you only get about 1/9 of the duration. So a 1 second ping on 2 meters will be around about 100 milliseconds on 70 centimeters. It's even worse for signal strength because that's proportional to that wavelength cubed. So a third times a third times a third is only a 1/27th of what you'd get on 2 meters. So it's going to be around about 15 dB weaker on 70 centimeters than it would have been on 2. Now, I'm very proud of this. This is one of my own recordings. Back some years ago, during the Orionid meteor shower, I operated right through the night with Ari down in Melbourne. We both ran simultaneously on 2 bands. So we had 70 centimeters and 2 meters running side by side, 2 transmitters, 2 linears, 2 amplifiers, 2 computers. And in the middle of the night, during the meteor shower, we both saw equivalent to this at various times. This was a 2-meter burn that came in. It's lasting at least 15 seconds at very high amplitude. And at exactly the same time, there was this tiny ping appeared on 70 centimeters, 100 milliseconds. It was enough to have a contact, and we did complete eventually on both bands. And I've never seen this recorded by anybody else, but it just shows the effect of going up in frequency. So that's the real thing. That's why this happens. If you go in the other direction down to 6 meters, of course, it works in your favor. Now the wavelength is 3 times longer, so the pings will last 9 times longer. 1 second ping on 2 meters will equate to at least a 10-second ping on 6 meters, and it will be 15 dB louder than it would have been on 2. So meteor scatter on 6 meters is really easy. In fact, it's close to the perfect wavelength to do meteor scatter. At the end of the day, though, a 2,000 kilometer contact on 6 meters is not that rare. There's lots of ways you can do that, but a 2,000 kilometer contact on 2 meters is still something worth writing in the logbook. Here's an example of a 6-meter ping, or burn if you like. And this one's extending for the full 30 seconds. In fact, it's not even reaching its peak at 30 seconds and probably went on for another 1 or 2 periods after that. So that's the sort of equivalent that you get on the lower band. So what's new out there? What else have we got to do? Well, as I said, the MSK144 as a mode took over from all its predecessors in about 2018, but I don't think this will be the last mode we see. There's still development going on. There's still room for improvement, and I'm fairly sure that in the course of time, there will be even better and even more sensitive modes to make this even easier to do. There's also several platforms where you can get access to this software. The two that you need to know about is WSJTX, the current version of Joe Taylor's software, and MSHV, which is the alternate, which comes out of Europe. Both of the authors are high-ranking scientists, and both of them are radio hams, and both of them have given this software, the suites of software, to the amateur service for free. You just have to do a Google to find these 2 bits of software if you don't already have them. Now, there is interest occurring where Meteor Scatter is combined with other modes of propagation. I've mentioned working 6 meters and 2 meters to New Zealand using combined Meteor Scatter and tropo ducting. Meteor Scatter and sporadic E does happen occasionally. You can see that. One interesting thing is Meteor Scatter and TEP, trans-equatorial propagation, occurring at the same time. You see this on 6 meters frequently. TEP is the commonest mode that you would be using for propagation if you work into Japan or into Asia on 6 meters. This is the double caudal F layer hop across the equator, and that's usually how you work into Japan on 6. If you monitor the Chinese television transmitters on 50 megs that are still there as an indicator that propagation's about to start, before TEP becomes apparent, you often see meteor pings appearing on the video carriers. And this is because Meteor Scatter's filling in the gaps that TEP hasn't quite reached. And finally, Meteor Scatter and EME happens because occasionally after the moon is set over the horizon or before it's actually risen, you can get meteor pings on EME signals because they're filling in the gap before the moon has actually risen over the horizon. So in conclusion then, what have we got? So Meteor Scatter is a mode of propagation. It's not a mode of communication, it's a mode of propagation, and it's always there. And it allows us to achieve long distances on VHF bands, even when there's no other propagation available, when the bands are dead. So you can regularly have QSOs on 2 meters out to 2,000 kilometers, sometimes more. You can achieve that with ordinary equipment and antennas and power, nothing fancy particularly required. It's not really a weak signal mode at all. It's just a short signal mode. And as we've talked, there are some spectacular results that you can achieve during meteor showers, which are all too frequent. So, gentlemen, at that point, thank you very much for listening to me tonight. I'm happy to try and take any questions and fill in the best I can. And I'm very grateful for this opportunity. And thanks again for listening.
You're awesome. Thanks, mate.
Is anything anybody wanted to ask at all?
There is one question, Kevin, on the YouTube, which is, if VK4s are transmitting in the second period, have there been any VK4 to VK4 QSOs, say Brisbane to Cairns?
Well, yes, you can do it, but you're not going to be popular if you try and do it during one of those activity sessions, because one or other of you is going to have to be in the wrong period for the general activity. But we do it. We just either go to a secondary frequency, and there is a secondary frequency on 2 meters at 144.350, or you do it outside of those normal operating periods. But I've worked up to Cairns. As long as you're inside that 2,000 kilometer impossible zone, you can do it. In fact, shorter distances can be done where the paths don't exist. So you can go across mountain ranges, for example. I can work into Rockhampton, which is very difficult to do from here because of the mountains in the way. But you can do that on Meteor Scatter too.
question from this end, Kevin. Hopefully you can hear us.
Yes.
It's working here. Noting you said here everything's on the one common frequency.
Yes.
I know that WSJT has a mode built into it where you can tell it to QSY on reply.
Yeah. That's a very good question.
Has anybody done that here in Australia? I know it's done in the States.
No, that's not the way we do it here in Australia. If you're in Europe or you are in North America, that is the way it's done. You also call CQ on a common frequency, and part of the string that you transmit is the frequency that you're going to be listening to for your reception. And in fact, WSJT is capable, for example, of hopping the transmitters through the cat control to the frequency that station's expecting to get their returns on. So they spread themselves out over a number of different frequencies. Here in Australia, though, our population, our density of stations operating is so low that we're better off probably by staying all on the same frequency, because the overlapping signals are not that common. And being all on one frequency means you've got a higher chance of actually making contacts, because you can see the other stations as they're working each other. So you've got more idea who's on and what's working. But certainly if the density of stations was much higher, then we could operate into those split modes. I've never done it, but that's how it's done in Europe and in the North America.
Okay, I've got another question from Bert.
Hi Kevin, it's Bernard VK5ABN. I've
Hi
done
there.
fast CW in the 70s and 80s.
Yes.
And most of our contacts were pre-arranged scats. So
Yes.
do you have them for a particular station, like if you attempted something like, I don't know, Brisbane, New Zealand or something like that, which probably you want to optimize in the direction of the antenna and hoping to complete that circuit?
Yeah, good question. And there are plenty of people who will still, during the meteor showers, have contacts on SSB, because often the meteor pings are so frequent that they tail one into the other, and you can get almost continuous coverage. I've never done CW, but I've had maybe 3 or 4 SSB contacts. You sort of listen to a beacon at the far end, and the moment you hear it, you pick up the microphone and yell your call sign, and you can do it if you've got enough patience. But the digital modes have made it possible to do this any day of the week, even during non-showers. But you can still do it, and even you can do it during those sessions, but you'd probably want to go to a pre-arranged specific frequency between the two stations, and again, have some agreement on who's transmitting when, so that you might say, well, I'll transmit in all the odd number minutes and you transmit in all the even number of minutes, and we'll eventually work. Because if you're patient enough, it will work and you will get the signals through.
Okay, do we have any other questions from here on the floor? Yep.
There is one more question on YouTube for you, Kevin. What about multiple meteors at the same time? Is there anything that exists such as a double hop?
Well, I'm sure there has to be. I'm sure statistically that must happen. But seeing as that, at the best of times we're 100 milliseconds each, it's going to be a pretty rare and very, very evanescent, very short-living phenomenon. But it probably does happen. How we'd make use of it for communications is a very moot question. I have no idea. Perhaps it happens more often than we realize. You often see more than one meteor coming very close together and even tying one to the other. You can subtly tell when you've changed from one rock to another, because there's a little bit of Doppler shift, and you can tell that one return that you're getting, one ping is from a certain station is on a different rock from another, or a different trajectory, because the Doppler shift, which the computers tell you, they'll tell you what frequency they're receiving the audio tones on, is subtly different. And in fact, some meteors that traverse the sky, you get reflections from both ends of their track. So you get one ping, a gap, and then another ping from the same station with different Dopplers. So you know that one was when the meteor or the meteor trail was coming towards you, and one when it was moving away.
Okay, we've got another question at this end.
Yeah, hi, Bob, 5FO.
Hi there.
It seems like the timing for your activities, Saturday, Sunday, optimised north-south, us in South Australia, east-west.
Well, of course, South Australia is not east, is not west of me. It's sort of southwest, and
But we are
and I'm to your
definitely
northeast.
west. We are most definitely west of VK3
Yes, you are. Yes,
and
you are.
VK7 and VK2, arguably.
But from South Australia, Meteor Scatter's probably not the mode of propagation that you need to work that path. You could probably do that better with just Tropo, and certainly the protocols that we run are not very supportive of those shorter ranges because they're pushing you all into the same period. So it's going to be difficult for you, but it will work. The principle is that you aim your antenna more or less in the direction of the station you're trying to work. And when you put in the call sign and the grid square of the station you're trying to work, there's a database in WSJT, for example, that knows what grid square it is. It will tell you what bearing you should take, and it will tell you which hotspot to aim at. But you're going to have to do it either outside the activity periods or on another frequency for those shorter hops.
Another question.
One thing I didn't mention, of course, is that there is a minimum distance as well that Meteor Scatter starts to fail on. If your other station is within 500 kilometers of you, it starts to get more and more difficult again, predominantly because you would need quite an amount of elevation to optimize the signals coming in from higher angles of elevation. So generally, below 500 kc, 500 kilometers starts to get really difficult again. And the gap between 500 and 1,000 is the really easy zone. And after that starts to get difficult again.
Just having done the sums on my head, I'm just wondering, VK 5 to 6 would almost be too far to Perth, wouldn't it?
I think you're out of range there.
Yeah, I think we just passed. Do we have any other questions here? Okay, the guys on Zoom.
Yeah, I've got a quick one.
Yep.
Has Kevin, is there a list or a website or something like that where you've got the list of the north-south beams and the frequencies and that sort of thing we can refer to at all?
There is. You will find there's a Facebook. There's a bit of social media stuff up there. There's a Facebook page where all the common operators post their intentions. The other facility that's really useful is the VK Spotter. In fact, most of the Australian Meteor Scatter stations all log on to the spotter so you can see who's on, and they post the completed contacts so that you can see who's working who else, and certainly gives you an idea how well it's running on that day. And the back chat with the chat facility, people make comments to whether this is a good day or a bad day, whether the meteors are running hot or whether they're not. But Meteor Scatters, and effectively it's a random process. Sometimes it's very quick, sometimes it's not. I think my record for a contact is 2 hours. That's how long it's taken to get the final report through. It is a random process. You need two things to be successful. You need to have insomnia and you need to have patience, because you're going to have to get up very early and be pretty patient waiting.
I'm going to fit right in. Another question I'm going to ask. How much power do you need on 6? 2 elements cut it.
Yeah, it would. If you can run 120 watts on 6 with 2 elements, you'll absolutely zoom it in on Meteor Scatter. Even when the band is completely dead, when there's nothing else to be heard, Meteor Scatter will be there in the mornings.
Give it a try now.
Give it a try.
Just another comment, Kevin, on YouTube from VK4CZ, who says Peter VK5 PJ is a regular on Meteor Scatter into VK4 on both 6 and 2 meters.
Yep, he certainly is.
And there is a question.
I knew Pete was.
And there is a question: can Meteor Scatter be done on HF? And if so, what is a common frequency?
Okay, that's a very good question too. It does work on HF, but that relationship between frequency and quality signals, it doesn't extend forever. It does work on 10 meters. Scott 4CZ and I have had a number of contacts with other stations down south on 10. It is quite difficult. The signals are weak and they're not as long as you might predict. Below 10 meters, I don't know. I've never tried below that. And there is no spot frequency that's in the band plans or commonly used. So people who are going both to 70 centimeters or down to 10 generally make up their own mind, and it's done by arrangement between the two stations. 28230 is actually a slow scan frequency, so you may not you may upset somebody going down there. But when I go on to 70 centimeters, I use 432 230 because it's as good as any other frequency.
There's other questions online. If Derek TCP, you want to unmute and ask a question?
Yeah, no problems at all. Thanks, Kevin, for the presentation, mate. I'm just curious. Obviously, well, not obviously, but the satellite communities move towards an idea of a two-line element, and also augmenting some of that data with laser ranging and other higher speed acquisition methods. Is that sort of ever been considered in regards to Meteor Scatter?
I don't think it has. I'm certainly not aware of anybody that does that. There are facilities that give you some clues. And the easiest one is your diary, because that tells you very quickly when all the meteor showers are coming, and they are incredibly predictable. There's also two other services that you can access online. There's a Canadian meteor radar system that runs 24/7 and actually maps out the heavens and collects data over a 24-hour period of the of meteor activity, albeit for the northern hemisphere. But it certainly shows you, for example, when the Orionid shower is starting and building up, or the Geminids, for example. And there's also another facility that we use in meteor showers, where you put in your grid square, and the grid square, the station at the other end, and it shows you when the constellation is above the horizon. If you want more information on that, I put it extensively in a series of articles that I put into AR magazine with all the links to that. It's worth having a look at that introductory series of articles if you've got them. But that will tell you. We use that in Australia. I can see, for example, although I can see, for example, the Orionid meteor shower, that in Tasmania it's beyond the horizon, so you don't get you're not going to get enhancement. And it shows you which paths are going to be, whether it's an east-west path that's going to be augmented or the north-south path, and they're very clever, and probably beyond this talk tonight. But it was covered in some of the previous articles, as I say, in AR. It's worth if this has interested you tonight, it's worth having a look at that series of articles and looking at some of the links.
Thanks, mate. Cheers.
There you go. Is there anyone else on Zoom who'd like to ask a question? Anybody here?
Yeah, another quick one from VK5 NET.
Okay,
Kevin, just wondering, is it such a on the foundation? So is there any such thing as a QRP meteor scatter?
You can use QRP, but generally it just makes it very, very difficult. Unlike most areas of radio, where if you put 3 dB more in at one end, you get 3 dB more out at the other end, Meteor Scatter doesn't work like that. Because there's a function of both time and amplitude to get decodes, as you go down in power or use the wrong polarity of antenna, it starts to get really, really hard. So people can run 20 watts, and I've had a few concerts, they're running 20 watts to a vertical because they want to try it out, but it's really hard for us at the other end, I can tell you. They seem to receive okay, but it's a struggle to get the signals up. So it does make things harder for you. The more power that you can run, the better it's going to be. And so most people who have a go sensibly run something in excess of 50 watts on either band. That's okay. That's good. And 50 watts and an 8-element Yagi, you're in the ball game. You got skin in the game if you do that. If you can run 120, it's not just 3 dB better, it's a lot more. You get a lot more at the other end because you get both larger amplitude and more time to do the decoding in. It's the area under the curve phenomenon of the received signals.
Okay, do we have any other questions here? Yep.
G'day, Kevin. Mark, 5AVQ.
Hi, Mark.
How you doing?
Good, mate.
Going to see you in June?
I'll be. It's going to be November, I think.
Ah, right.
They've just announced that Gibbs Tech's going to be in November this year, so I hope we see all of you.
We'll see what happens. Yeah, that limit. I'm sure we'll be vaccinated. The introductory articles, just was that just trying to remember when they were. fairly recently, wasn't it? Yeah, in the JRs.
I'm sorry, Mark. I'm not getting you. Breaking up a little bit. I heard you say about
articles,
yes.
Introductory articles. How far back were they?
Oh, they're in the last 12 months. There's a 4-part series that I wrote for AR. Over there.
I remember those. I was just trying to remember how far back they were.
So I've been doing the monthly column, and there's lots of different topics that have been covered over the 10 years I've been writing for that. But the introductory ones, which you probably find all of the references, they're in the last 8 months or so. So it's they're quite well worth a look for the references at least.
Gotcha. Okay, and the a meteor shower. Is there
Yes.
any particular? They usually publish it'll be over 2 or 3 days. Is there any particular day on average that you find better for amateur radio work?
Okay, that's a good question too. And the different showers are quite different. They've got different characteristics as well. I actually have an app on my mobile phone which tells me when the showers are coming up. Some of them are quite broad. They will cause enhancement over long periods of maybe 4 or 5 days either side of the peak, and some of them are incredibly short where you're only going to get enhancement on the one day. That sort of information is out there and available, and there, as I say, there are very easy apps that you can even have on your phone. Most of the information that's published about meteor showers, of course, is aimed at people that are interested in looking at meteors for their optical effects. They want to see shooting stars, and most of it is aimed at people who live in the northern hemisphere. So there's a few catches there, because there are some major showers in the northern hemispheres that are too far north of us to be able to be visible down here. So you can see them in Queensland, but not in the southern states.
Okay, thanks. That was what I was thinking. The radio would be different to the optical, so what's published.
Yeah,
thanks
that's true.
73's for me.
Okay, do we have any other questions here on the floor? Yep. Alan? Jim?
G'day, Kevin. Ian, VK5ZD.
Hi, Ian.
Hey, just a thought. Has anybody tried, imagine like a couple of stations in Brisbane or in Queensland, maybe say a couple of 100 kilometres apart, both beaming south to see if you can bounce off a meteor that maybe is 500 kilometres away? Has anyone tried that?
Well, we always beam south from up here because that's where we think our targets are, I suppose, unless we're trying to work somebody in Kent. We've only got one station in VK4 who's north of us, unfortunately, at the current time, who's active. But we've tried, we'd be very keen to try and work stations who are either further west or further north of us. There's just nobody there.
Yeah, I'm thinking of you know, does the RF scatter backwards?
Oh, yes, it does. Yes.
So,
yes,
I mean, obviously,
it certainly does.
One station would have to be on a different period to the other.
Yeah.
But, you know, like two Queensland stations work each other by bouncing off something that's.
Yeah. Yeah, that certainly happens. Backscatter certainly does happen. If for any reason you drop transmit and you don't transmit every period, so you're hearing all the local stations, you often see backscatter coming back up from traces where the station that's clicking over at about an S1 suddenly goes up to S9 or 20 over for 100 milliseconds. So backscattering does occur, and we do use that to hop over mountain ranges. There's a couple of stations who are out of range of us here by sort of traditional meteor scatter, and we can, or traditional tropo, you can't get through, but you can hop over the hills over a path that you can't otherwise use.
Right. Okay, thank you.
Thank you. Any others?
It's presentation there.
All right, thank you, Trevor. Is there a question you'd like to ask as well, or?
No, not really.
Not a problem. Thank you very much.
Okay. All right.
Anybody else on Zoom?
A quick
Anybody
one
else here
from
on
me,
the floor?
if I may, Grant.
Yeah, go ahead.
Good evening, Rob Milliken, VK1 KRM. I'm interested in antennas.
Yes.
And what I haven't heard tonight, and it's probably just through my lack of either listening or this is my first intro into the subject, and it's been excellent, thank you. What actually are the parameters of the antenna in terms of, can I call it the elevation as well as the azimuth? The azimuth you mentioned is sort of
Yep,
plus or
yep.
minus 10 degrees.
Yep, we did touch a little bit about elevation. Generally, you don't need. So you don't need elevation control because the signals that you're interested in from the longest, the furthest stations away are going to be ground scraping. So they're coming in at 0 elevation anyway. In terms of antenna gain, an 8-element Yagi is what most people find to be the sweet spot. If you've got antennas that are much bigger than that with a narrower RF aperture, you tend to lose more signals that are coming in off the edge than you gain by the additional signal strength.
Yep.
Now, in theory, if you stack antennas vertically, if you stack 2 Yagis vertically, you can get more gain while still maintaining the same aperture. And in an ideal world, that's what I would do. What that will cost you, though, apart from the mechanics of doing that, is that stations or signals that are coming in with some elevation, you're going to lose because it generates its gain by pulling the beam in that way rather than that way.
Yes.
So, but stacking antennas vertically should, in theory at least, allow you to have more gain and be beneficial.
I was just thinking about using a corner bay array, because a corner bay reflector will, from my understanding, give you a reasonably broad azimuth.
Yep.
If you compress the elevation.
Yep. And that would work. That would work. It's going to be a big antenna, but it would certainly work.
Thank you.
Okay, we've got another question down here.
Hi, it's Mark, VK5QI here. So, we've talked about how WSJT has kind of brought EME to the realm of the common operator.
Yep.
And I've seen contacts made on EME with ridiculously small stations,
yep.
like dipoles. Obviously, the guy on the other end's pulling the weight.
Yep.
But what do you know of has been kind of the smallest station for a meteor scatter contact?
That's a good question. I'm not sure I've got any information on that. Certainly, when I started playing with Meteor Scatter, I was only running 50 watts. So that's certainly good enough to have contacts with. And I think you could I'm certain you could do it with a 2 or 3 element Yagi. All it does is makes it more difficult for the stations at the other end.
You're running the big beam.
But certainly during meteor showers, when the signals are frequent and intense, you would certainly be able to have contacts. And give it a go. Just come up on a Saturday or Sunday morning, put your receiver on and see what you can hear. Because you'll be surprised. Meteor Scatter is not a weak signal mode, I can assure you. Sometimes the signals make the S meters jump up quite a long way up the scale. It's a short signal mode, not a weak signal mode.
So I'm just curious, Kevin, what time do you need to start in the morning?
I mean, your ideal is that you want to be on the air before dawn. So you set the alarm clock, you make the coffee, and you come down to the shack while it's still dark. And that's realistic. That's going to be around about 2000 Zulu most times of the year.
Oh, is that all?
That's all. So
I could do my 160 while I'm waiting for 6 to do things.
God gracious me, trying to get you VK5s out of your pit first thing in the morning seems to be the hardest task. I don't know. Can't get you on the air.
Now.
Don't forget, I was a VK5 for 10 years. I know what it's like down there.
We gave you honorary status.
True. Anyway, thank you very much for listening. It's been a pleasure. It's been an interesting experience doing a lecture when you can't see the other end. So I'm very grateful for that opportunity, and thanks for inviting me.
Thank you very much, Kevin.
Thanks, Kevin. It's been a pleasure.
Round of applause, please, everybody. Thank you. Okay, so Hayden, if you want to maybe drop the stream.